In 1940, the F4U Corsair stunned the aviation world by achieving a top speed of 446 mph, becoming the first single-engine fighter in US history to break the 400 mph barrier in level flight. This achievement cemented its reputation as one of the most fearsome fighter aircraft of World War II. But was the Corsair truly the apex of wartime aviation, or did its groundbreaking design come with critical flaws that threatened its legacy? With its iconic inverted Gull wing and the mighty Pratt and Whitney R2800 double Wasp engine, the Corsair epitomized the innovative spirit of 1940s engineering. Yet, its development journey was fraught with challenges from landing gear issues to pilot visibility concerns. Could these hurdles have overshadowed its triumphs in speed and combat? Let's dive into the engineering marvels and controversies surrounding the legendary F4U Corsair. Revolutionary design requirements. In February 1938, the U.S. Navy Bureau of Aeronautics outlined a set of ambitious requirements that would lay the groundwork for the development of one of the most iconic fighter aircraft in aviation history, the F4U Corsair. These specifications reflected the Navy's vision for a next-generation aircraft capable of dominating the skies in both performance and versatility. At the forefront was the demand for unparalleled speed to achieve the highest attainable velocity to outpace potential adversaries. Equally critical was the need for exceptional low-speed handling, requiring a stalling speed of less than 70 mph to ensure safer carrier landings and improved maneuverability during combat. The Navy also envisioned a fighter with substantial operational range, specifying a distance of at least 1,000 miles to support extended missions and patrols. Armament was another cornerstone of the design, with the aircraft needing the capacity to carry 4 guns, or an alternative configuration of 3 guns with increased ammunition reserves, ensuring sustained firepower in intense engagements. Furthermore, the specifications included provisions for carrying anti-aircraft bombs, highlighting the multifaceted role the aircraft was expected to fulfill. These demanding criteria not only shaped Corsair's engineering but also underscored the Navy's determination to push the boundaries of aeronautical innovation. The Navy's requirements pushed the boundaries of aircraft engineering, demanding a fighter that could outperform existing aircraft while maintaining carrier compatibility. The specifications led to the selection of the most powerful engine available at the time, the Pratt Whitney R2800 double Wasp, which delivered 1,850 horsepower for takeoff. The development team encountered substantial technical challenges in adapting the F4U Corsair to meet the stringent demands of carrier operations. Designing an aircraft capable of balancing high-speed performance with the precise low-speed handling required for carrier landings proved to be a complex endeavor. During early test flights, several critical issues emerged, threatening the feasibility of the Corsair as a carrier-based fighter. One significant problem involved the aircraft's hydraulic cowl flaps, which, during operation, allowed oil to seep onto the windscreen, severely impairing the pilot's visibility, a critical safety concern during landing approaches. Another issue arose from the undercarriage, which exhibited problematic rebound characteristics upon landing, making the aircraft difficult to control during the critical moments of touchdown. Perhaps most concerning were the wing stall problems encountered during slow-speed carrier approaches. These stalls, caused by the unique aerodynamic behavior of Corsair's wings, posed a significant risk of loss of control and underscored the challenges of marrying speed with stability in a single design. Resolving these issues required innovative solutions and iterative testing, showcasing the resilience and ingenuity of the engineering team determined to make the Corsair a cornerstone of naval aviation. The incorporation of the powerful Pratt Whitney R2800 double Wasp engine into the design of the F4U Corsair brought with it a host of unique engineering challenges. This massive radial engine demanded an equally imposing 13-foot, 3-inch 3-bladed propeller to harness its tremendous power, a feature that fundamentally influenced every aspect of the aircraft's design. Balancing the engine's immense output with the aircraft's overall weight and structural integrity became a central focus for the engineering team, driving them to devise a series of innovative solutions. One of the most striking design features to emerge from this process was the inverted Gull wing. This distinctive configuration allowed for shorter and lighter landing gear by reducing the angle at which the wings attach to the fuselage, enabling the propeller to clear the ground without requiring excessively tall and heavy gear. This innovation not only solved a practical problem, but also contributed to the Corsair's sleek and aerodynamic profile. To further address weight concerns, engineers adopted advanced manufacturing techniques, including the use of spot welding for the aircraft's aluminum panels. This method reduced the overall weight of the airframe while maintaining structural integrity, a critical factor in maximizing the fighter's speed and agility. Another clever adaptation involved the placement of oil coolers within the anhedral section of the wing, a design choice that utilized airflow through this area to regulate engine temperatures efficiently. The design team maintained a strict focus on performance, adhering to Chief Engineer Rex B. Beisel's principle that speed is king. This dedication to performance resulted in the first U.S. Navy aircraft to feature landing gear that retracted into a fully enclosed wheel well, contributing to its exceptional aerodynamic efficiency. To meet combat requirements, the design incorporated additional features, including 150 pounds of armor plate and a 1.5-inch bulletproof windscreen. These modifications, while adding weight, were essential for survival in combat conditions while maintaining the aircraft's exceptional performance capabilities. The ingenious inverted gull wing. Among the most distinctive features in aviation history, the Corsair's inverted gull wing emerged from a crucial engineering meeting at Vought Aircraft. Chief Engineer Rex Beisel and his team conceived this innovative solution while addressing multiple design challenges simultaneously. The inverted gull wing's effectiveness stemmed from its unique approach to aerodynamic optimization. The wing met the fuselage at a 90-degree angle, creating an optimal junction that significantly reduced interference drag. This perpendicular intersection eliminated the need for complex wing root fairings, while the wing's distinctive bend maintained ideal airflow characteristics across its entire span. The design's aerodynamic brilliance lay in its dual functionality. It not only solved the ground clearance challenge but also enhanced the aircraft's overall performance. The wing's anhedral center section allowed for optimal wing fuselage integration, while the outer panels provided stability during carrier approaches. To successfully integrate the innovative and complex gull wing design of the F4U Corsair, the engineering team devised several groundbreaking solutions that pushed the boundaries of aeronautical engineering. These innovations were essential not only to accommodate the unique structural demands of the inverted gull wing, but also to enhance the aircraft's overall performance and functionality. One critical advancement was the incorporation of slotted flaps into the curved gull wing section. This design improvement significantly enhanced the aircraft's low-speed handling characteristics, particularly during takeoff and landing on the short and often unpredictable decks of aircraft carriers. By directing airflow more effectively over the wings at low speeds, the slotted flaps improve lift and reduce the risk of stalling, addressing one of the most pressing challenges in adapting high-performance fighters for carrier operations. Another remarkable solution was the development of a sophisticated landing gear retraction mechanism. The engineers created a system in which the gear folded back into the wing and simultaneously rotated 90 degrees to fit snugly within the slim confines of the gull wing structure. This innovative mechanism minimized drag and preserved the aerodynamic integrity of the design while maintaining the strength and reliability needed for carrier landings. In addition to addressing aerodynamic and structural challenges, the team optimized the Corsair's cooling system by integrating leading-edge air intakes at the point where the wings joined the fuselage. This clever placement capitalized on natural airflow patterns to direct air efficiently into the cooling system, ensuring the powerful R2800 engine remained within optimal operating temperatures during intense combat or extended missions. The wing structure incorporated innovative stress distribution techniques, allowing it to maintain exceptional strength despite its complex geometry. The design team positioned the aircraft's armament outside the landing gear assembly in the folding section of the wing, while large oil coolers were efficiently housed in the wing roots. The construction of the inverted gull wing presented unprecedented manufacturing challenges. Vought's solution was the development of a massive jig fixture assembly, more comprehensive than any previously used in aircraft manufacturing. This specialized tooling enabled precise fabrication of the wing's complex curves and structural components. The manufacturing process required exceptional precision in fabricating the curved wing center section. The engineering team assigned their most skilled designers to tackle this challenge, resulting in an extremely strong structure built as a single unit with a lower fuselage. This innovative construction approach ensured both structural integrity and manufacturing efficiency. Under certain flight conditions, particularly during high-speed dives, the wing's leading-edge air intakes created a distinctive screaming sound, earning the aircraft its nickname among pilots. This characteristic became one of many unique features that distinguished the Corsair from its contemporaries. Powerplant engineering marvel. The heart of the F4U Corsair's exceptional performance lay in its powerplant, the formidable Pratt Whitney R20-800 double Wasp engine. This 18-cylinder, twin-row radial engine represented the pinnacle of American aircraft engine technology, delivering 1,850 horsepower for takeoff when first introduced. Integrating the powerful Pratt Whitney R20-800 double Wasp engine into the F4U Corsair posed significant engineering challenges, as its immense output demanded innovative solutions to maximize performance across a wide range of operating conditions. Central to the design was the engine's massive Hamilton standard hydromatic propeller, which measured an impressive 13 feet 4 inches in diameter. The engineering team developed a highly advanced two-stage, two-speed auxiliary supercharger system to ensure the aircraft could achieve optimal performance at varying altitudes. This system allowed the engine to operate efficiently under diverse conditions by providing 3 distinct operational settings. At high altitudes, where air density is significantly reduced, the system's high gear setting enabled the engine to generate maximum power, ensuring the Corsair could maintain superior performance even in thin air. For medium-altitude operations, the low gear setting adjusted the supercharger's output to match the engine's requirements, delivering consistent and reliable power. At low altitudes, where less supercharging was needed, a neutral setting minimized unnecessary strain on the engine while optimizing fuel efficiency. This sophisticated supercharging system exemplified the ingenuity and precision of Corsair's design, ensuring the double Wasp engine could deliver its full potential across the varied and demanding conditions of aerial combat. By addressing the challenges of integrating such a powerful and complex power plant, the engineers contributed to making the F4U Corsair one of the most versatile and effective fighters of its era. The R20-800's cooling system featured groundbreaking innovations in fin design. Engineers abandoned traditional casting methods in favor of precision machined cooling fins cut from solid metal cylinder head forgings. This revolutionary approach utilized an automated gang of milling saws that created thinner, closer pitch fins following the head's contour, significantly increasing the cooling surface area. The engineering team developed sophisticated power management systems to maximize the engine's capabilities. A notable innovation was the water injection system, introduced in later variants like the F4U-1A and F4U-1D. This system enabled war emergency power operation, boosting output to 2,250 horsepower. The system's activation mechanism was elegantly simple yet effective. Pilots would break a safety wire by advancing the throttle fully forward, engaging the water injection system automatically. As the Corsair evolved, so did its powerplant. The F4U-4 utilized the enhanced R20-800 Dembo engine, producing 2,100 horsepower at 2,800 RPM. The ultimate expression of the double Wasp potential came in the F4U-5, which employed the R20-800 and generating 2,450 horsepower, with water methanol injection pushing output to 2,850 horsepower. This continuous development of the engine system played a crucial role in maintaining the Corsair's edge in performance throughout its operational life. The R20-800's reliability proved as impressive as its power output. The engine's robust design and efficient cooling system enabled sustained high-power operation, crucial for both combat effectiveness and long-range missions. This combination of power and reliability helped establish the F4U Corsair as one of the most capable fighter aircraft of its era. Advanced materials and construction. The construction of the F4U Corsair showcased significant advances in aircraft manufacturing technology, particularly through its innovative use of materials and assembly techniques. The aircraft structure represented a departure from traditional manufacturing methods, employing new spot welding techniques developed by the Naval Aircraft Factory to create robust aluminum skin and support structures. The construction of the F4U Corsair relied on the use of advanced aluminum alloys, meticulously chosen to meet the demanding requirements of naval aviation. These materials were selected for their exceptional strength-to-weight ratio, ensuring the aircraft maintained structural integrity while remaining lightweight enough to achieve superior performance. The alloys also offered excellent corrosion resistance, a critical attribute for enduring the harsh, salt-laden environments encountered during naval operations. Additionally, the materials provided high fatigue resistance, an essential quality for withstanding the repeated stresses of carrier landings, which subjected the airframe to intense forces. To further enhance durability, the aluminum alloys were engineered with heat treatment capabilities, allowing the construction to endure the rigorous conditions of combat and operational use. A unique aspect of the Corsair's construction was its hybrid approach to materials. While primarily metal-based, it was the last American-produced fighter aircraft to feature fabric skinning on the outer wing panels after the main spar, as well as on the ailerons, elevators, and rudder. The aircraft's structural design incorporated sophisticated stress distribution techniques, particularly in the fuselage panels. Engineers employed newly developed spot welding methods, largely eliminating the need for rivets in large fuselage sections. This approach not only reduced weight, but also enhanced the structure's ability to withstand the significant stresses of carrier operations and combat maneuvers. The stress distribution analysis was particularly critical in the wing structure, where the complex inverted gull wing design required careful attention to load paths. The manufacturing process utilized a comprehensive jig fixture assembly, more intricate than any previously used in aircraft manufacturing. Throughout the development of the F4U Corsair, weight reduction remained a critical priority, particularly for land-based operations where certain naval-specific components were unnecessary. To address this, the Bureau of Aeronautics approved various measures to streamline the aircraft. By removing the catapult hooks, the engineers were able to save 16 pounds, while eliminating the arresting hooks further reduced the weight by an additional 32 pounds. Other associated gear related to these components was also omitted, contributing to further weight savings. These adjustments exemplified the meticulous effort to optimize the Corsair's performance by shedding unnecessary weight, without compromising its operational effectiveness in specific roles. For shore-based operations, 965 FG-1As were built without hydraulic wing folding mechanisms, significantly reducing complexity and weight. The engineering team also developed field modification kits, allowing the removal of carrier-specific equipment, optimizing the aircraft for land-based operations while maintaining its structural integrity. The manufacturing process incorporated innovative techniques for joining aluminum components, including a variable lateral control linkage system that enhanced maneuverability while maintaining structural efficiency. This attention to manufacturing detail and material selection contributed significantly to the Corsair's exceptional performance capabilities. Aerodynamic breakthroughs. Extensive wind tunnel testing at Langley Memorial Aeronautical Laboratory proved instrumental in shaping the F4U Corsair's exceptional performance capabilities. Operating around the clock during World War II, these tests would establish new benchmarks in aircraft development. The Langley 7 by 10-foot tunnel facility conducted comprehensive tests using a 0.182- scale model of the F4U-1, focusing particularly on external store configurations and their impact on performance. These tests yielded crucial data about the aircraft's behavior at various speeds and configurations. The facility's massive 30 by 60-foot open throat could accommodate aircraft with wingspans up to 40 feet, while twin 4,000 horsepower electric motors drove air through the tunnel at speeds up to 118 mph. The F4U Corsair incorporated a range of innovative features designed to minimize drag and enhance aerodynamic efficiency, ensuring peak performance in combat. One of the key advancements was the integration of oil coolers within the wing's anhedral section. The design eliminated unnecessary protrusions that could disrupt airflow and create drag, by utilizing openings along the wing's leading edge instead of scoops. Another notable feature was the perpendicular junction between the wings and fuselage, which removed the need for drag-inducing wing fillets commonly used to smooth transitions between these surfaces. This clean connection improved the aircraft's overall aerodynamic profile while maintaining structural integrity. Additionally, the Corsair became the first U.S. Navy aircraft to feature fully enclosed wheel wells. The NAK's drag reduction efforts significantly enhanced both speed and range, providing Allied pilots with crucial advantages in combat situations. The aircraft's streamlined design enabled it to maintain controlled flight at both high speeds and the slower speeds required for carrier landings with a full flap deployment of 50 degrees. The F4U Corsair delivered extraordinary performance capabilities that set it apart as one of the most formidable fighter aircraft of its time. It achieved an impressive maximum speed of 453 mph, showcasing its ability to dominate aerial engagements with unmatched velocity. Its cruising speed, measured at 215 mph, allowed for efficient long-range operations, contributing to its versatility in various mission profiles. Additionally, the Corsair boasted a combat range exceeding 1,500 miles, ensuring it could undertake extended missions with ease, from offensive strikes to patrol duties. During full power dive tests, the aircraft achieved speeds up to 550 mph, though such velocities resulted in control surface stress and occasional engine complications. Engineers addressed these challenges through systematic improvements, including the addition of a small 6-inch stall strip to the outer right wing's leading edge, which resolved potentially hazardous high-speed handling characteristics. The wind tunnel testing program revealed that the incremental drag coefficient from external stores could accurately predict the aircraft's maximum attainable Mach number in flight. This data proved invaluable for operational planning and helped establish the Corsair's reputation for exceptional speed and maneuverability. The aircraft's advanced aerodynamics, combined with its powerful engine, made it the fastest naval aircraft in the U.S. inventory. Landing gear innovation. The landing gear system of the F4U Corsair represented a significant advancement in naval aircraft engineering, featuring self-contained oleo struts that operated independently from the main hydraulic system. This innovative design proved crucial for the aircraft's successful adaptation to carrier operations. The F4U Corsair featured groundbreaking landing gear innovations, including a sophisticated oleo strut system and an advanced retraction mechanism. The oleo strut system, designed for precise pressure management, played a crucial role in ensuring smooth and controlled landings. According to the initial specifications, the strut extension was set between 7 and 7.5 inches, with air pressure maintained at 300 psi, with a tolerance of 25 psi. Specialized servicing procedures were implemented to maintain optimal performance and reliability. During early carrier qualification tests, VF-17 squadron pilots identified an opportunity to enhance landing characteristics. By increasing strut pressure from 40 to 60 psi and incorporating anti-bounce cylinders, the team significantly improved the Corsair's behavior during carrier landings, mitigating bounce and increasing stability upon touchdown. The Corsair also introduced a revolutionary landing gear retraction mechanism, becoming the first U.S. Navy aircraft to feature gear that retracted into fully enclosed wheel wells. This system was engineered with several innovative features. The strut doors provided individual enclosures for each wheel when retracted, maintaining a streamlined profile. The landing gear utilized a 90-degree rotation during retraction, positioning the wheels atop the lower strut to minimize space requirements. Rectangular doors sealed the wheel wells completely, further reducing drag and enhancing aerodynamic efficiency. This swiveling, aft-retracting design bore similarities to the system employed in the Curtiss P-40 and later influenced the landing gear design of the Grumman F6F Hellcat. Together, these advancements in strut technology and retraction mechanisms exemplified the Corsair's role as a pioneer in naval aviation engineering, blending performance with functionality to meet the rigorous demands of carrier operations. Initial carrier landing trials revealed significant challenges that required immediate engineering solutions. The landing gear demonstrated problematic rebound characteristics during deck landings, causing the aircraft to bounce dangerously. Engineers tackled these issues by making several crucial modifications. They introduced a bleed valve in the landing gear legs to slowly release hydraulic pressure during landings, increased the oleo pressure to 350 psi through Bulletin 438, which set a new standard distance of 7-7.25 inches between pivot centers, and added anti-bounce cylinders and valves to the struts. The engineering team faced particular challenges with the aircraft's behavior during slow carrier approaches. The combination of the inverted gull wing design and landing gear characteristics initially made the Corsair challenging to land on carriers. However, the implementation of these modifications, along with proper pressure management in the landing gear system, eventually solved the notorious deck bounce issues. The demands of carrier operations required the landing gear to withstand significantly higher stresses than conventional land-based aircraft. This led to reinforced structural components and the installation of a tail hook system, making the F4U Corsair's landing gear among the most robust of its era. Combat systems integration. The integration of combat systems in the F4U Corsair demonstrated exceptional attention to weapons engineering and survivability design. The aircraft's armament configuration evolved significantly from its prototype stage, which initially featured two 12.7mm machine guns in the wings and two synchronized 7.62mm guns above the engine. The production F4U-1 featured a robust armament package of 6.0 caliber Browning M2 machine guns with 3 mounted in each wing. The ammunition capacity was precisely calculated, 400 rounds for each of the 4 internal guns and 375 rounds for the 2 external guns. This configuration proved highly effective, leading to the Corsair achieving an impressive combat record of 2,140 enemy aircraft destroyed against just 189 losses during the Pacific campaign. The weapons system of the aircraft evolved significantly over time, with several notable iterations that enhanced its combat capabilities. The introduction of the F4U-1C variant marked a major step forward, as it was equipped with 4 powerful 20mm cannons, greatly improving its firepower for engaging both air and ground targets. Following this, the F4U-1D variant brought further advancements, particularly in its ability to carry additional stores, allowing for greater flexibility in mission planning and a wider range of ordnance. As the aircraft's design continued to progress, later variants were engineered to support even heavier payloads. These variants were capable of carrying up to 3 1,000-pound bombs, ideal for striking high-value targets, alongside 8 5-inch rockets, further enhancing the aircraft's versatility and effectiveness in a wide array of combat situations. These upgrades collectively transformed the aircraft into a formidable weapon on the battlefield, capable of delivering significant firepower in various combat scenarios. The engineering team developed an innovative ammunition container system that significantly enhanced combat efficiency. Initially, the F4U-1s featured 12 unique ammunition containers, 6 per wing, with none being interchangeable. By December 1942, following the Navy's Bureau of Aeronautics request, Vought redesigned the system to allow for container interchangeability. The enhanced design led to several important changes, particularly in the wing position and container configuration. The left wing now featured 5 interchangeable positions, offering greater flexibility, while the right wing also incorporated 5 interchangeable positions. Additionally, the number of container types was reduced to 2 per side, streamlining the overall setup and improving operational efficiency. This redesign allowed Container 1 to be swapped with Container 3 and Container 2 with Container 4, significantly improving maintenance efficiency. By late 1943, each aircraft was equipped with a spare set of ammunition containers, enhancing operational flexibility. The F4U Corsair's survivability features set new standards in aircraft protection. The production model incorporated substantial armor protection, including a large self-sealing fuel tank positioned over the wing in the fuselage, 150 pounds of armor plate for critical components, and one 5-inch bullet-proof windscreen. The aircraft's structural design prioritized vulnerability reduction, enabling it to withstand significant combat damage while maintaining critical functions. This approach proved highly effective, as the F4U demonstrated superior survivability compared to other fighters of its era. The US Army Air Force acknowledged that the Corsair could absorb greater battle damage than even the notably robust P-47 Thunderbolt. The Pratt Whitney R2800 engine contributed significantly to the aircraft's survivability, maintaining power output even with multiple cylinders damaged by enemy fire. This resilience, combined with the aircraft's robust structural design and advanced protection systems, made the F4U Corsair one of the most survivable fighter aircraft of World War II. Performance optimization. Performance optimization of the F4U Corsair stands as a testament to continuous engineering refinement throughout its operational life. The aircraft's capabilities evolved significantly through various modifications and improvements, establishing new benchmarks in naval aviation performance. The F4U-1's performance characteristics displayed an exceptional balance between speed and maneuverability. At sea level, the aircraft reached a maximum speed of 311 mph, and at its critical altitude of 24,350 feet, it achieved an impressive 38 mph. This remarkable performance was the result of the engineering team's meticulous optimization of several key parameters. The aircraft's takeoff speed was 82 mph, and it was capable of reaching a service ceiling of 36,200 feet, showcasing its impressive operational range and high-altitude capabilities. The F4U-4 variant further enhanced these capabilities, demonstrating superior roll rate and maintaining exceptional control responsiveness even at high speeds. The aircraft could achieve a 6% reduction in drag compared to contemporary fighters, enabling it to outperform many of its contemporaries in air combat maneuverability. The engineering team made significant strides in improving the climb rate performance with each successive variant. The F4U-1 initially demonstrated a climb rate of 2,890 feet per minute at sea level, and it was capable of reaching 10,000 feet in just 3.65 minutes. With a service ceiling of 36,200 feet, the aircraft gained a tactical advantage in high-altitude combat situations. Later variants, particularly the F4U-4, showed even more substantial improvements in climb performance. This model could reach 20,000 feet in just 10 minutes, a notable improvement compared to the 12 minutes it took for contemporary naval fighters. These enhancements were achieved through refinements in engine management and aerodynamic optimizations, further solidifying the aircraft's superior performance in various operational conditions. Range optimization was a key factor in the Corsair's success during Pacific operations. The engineering team implemented several innovative solutions to extend the aircraft's operational reach. The base F4U-1 achieved a maximum range of 965 miles at 5,500 feet, maintaining an average speed of 191 mph during maximum range operations. To further enhance this, engineers developed advanced fuel management systems that allowed for multiple endurance configurations. These included high-speed endurance at 21,500 feet for 0.86 hours, 90% high-speed endurance for 1.40 hours, and 75% high-speed endurance for 2.61 hours. At 5,500 feet, the aircraft could sustain maximum endurance for up to 5.05 hours. The F4U-1D variant, designed for operational flexibility, featured twin pylons to increase fuel capacity. Engineers also devised efficient cruise settings that balanced speed with fuel consumption, and the advanced fuel management systems optimized fuel use across different power settings, contributing to the aircraft's extended range and overall efficiency. The engineering team's focus on performance optimization resulted in remarkable combat effectiveness. The F4U-4 variant, for example, demonstrated a 10% top speed advantage over contemporary fighters. This edge in performance was crucial in combat scenarios, as the aircraft could maintain high speeds while preserving its maneuverability, giving pilots significant tactical advantages. Even under combat loads, the aircraft's performance remained impressive. Engineers carefully balanced power-to-weight ratios for different loadouts, reduced drag in various weapons configurations, and optimized fuel load distribution. The F4U could carry substantial combat loads without sacrificing performance, maintaining its ability to perform high-speed maneuvers, even when fully loaded. This was a testament to the success of the engineering team's optimization efforts. The F4U Corsair is a true engineering masterpiece of World War II, setting new standards in naval aviation with its unique Gull wing and powerful R2800 engine. The aircraft's remarkable performance, advanced manufacturing techniques, and innovative solutions for carrier operations made it a standout in combat, achieving an 11-1 kill ratio. The Corsair's legacy continues to inspire engineers and aviation enthusiasts worldwide. What's your take on the Corsair's impact on aviation? How do you think its design influenced future aircraft? Share your thoughts in the comments. Thank you for taking the time to watch the video. See you in the next videos.